Why is this important? There are various reasons. Many integrated circuits go into battery-powered applications. So clearly, you need to be very ultra-sensitive to power consumption of the chip. But even for those chips that don't go into battery-powered applications, power consumption is extremely important. For example, chips that go into data centers, where maybe the chip is an accelerator in a server. You have lots of these devices then going into a data center, and the power consumption in data centers is of great importance. It really affects the cost of the data center operation, and there's the carbon footprint issue of data centers. So power is very important even for chips that go into non-battery powered situations like data centers. And finally, any chip needs to dissipate the power that's being consumed. So power reduction is important even in chips that are not battery powered, where the dissipation of the power being consumed is critical, and sometimes it adds to the cost of the system. So for example, all our laptops have small fans built in. Some more advanced computers even have actual cold water going through the system to enable power heat dissipation. And so in situations like that, whatever can be done to reduce the power consumption really impacts the cost of the system. So power consumption is a very critical and very important topic in chip design, and techniques for reducing power consumption are very important to master to high quality chips. So to get started on this topic, the first thing to understand is that in a logic circuit, every gate is driving some capacitance. So as an example here, you see the 2-input AND gate U1 driving a couple of standard cells. One is a flip-flop, the other is a 2-input NAND gate. There's also the net connecting all the pins that U1 is driving. So the net N1 connects 3 pins. And if you look at the capacitance that U1 is driving, it comprises the capacitance of the net N1 plus the input pin capacitances of U2 and U3. And that's what I'm trying to show here, that U1, you can think of it as driving some load capacitance CL. And the load capacitance is based on, then the load capacitance has 2 components. One is the wire capacitance or the net capacitance. In this case, it is a capacitance of net N1. And then the pin capacitances of all the pins being driven by the driver. So in this case, the pin cap is the sum of the B pin of U2 and the D pin of U3. And so this is the total load capacitance of U1. At every instance in the logic circuit will have its own load capacitance that it is driving. And load capacitance is one of the important components in the equation for power consumption. The next thing is how often this is load capacitance being charged and discharged. So obviously the load capacitance will be charged low to high or high to low as the logic circuit operates. And what I'm showing here is that when this 2-input NAND gate U1 is, when its output is transitioning from low to high, which is the first picture on the left here, then charge flows from VDD to the load capacitance, and the load capacitance gets charged up. Okay, so as the output goes low to high, current flows from VDD through the 2-input AND gate and charges up the load capacitance. And when the output of the AND gate goes high to low, then the load capacitance gets discharged, and the same charge Q then flows from the load capacitance to ground. So during a low to high transition, charge Q flows from VDD to the capacitor, and from a high to low transition, the same charge flows from the capacitor to ground. So if you consider a complete pulse that goes from low to high and then high to low, you will see a charge Q flow from VDD to ground. Okay. So how much is this charge Q that goes from VDD to ground every time there's a pulse? Remember, the pulse is a combination of a low to high transition followed by a high to low transition. So that's a pulse. And in any pulse, a charge Q flows from VDD to ground. And that charge, the amount of the charge is CL times VDD by definition of capacitance. Right? So for every pulse, this charge Q flows from VDD to ground. Now, when you want to look at power dissipation, then we have to determine how many pulses there are per second. Okay. And since every time, so first of all, every time charge flows from VDD to ground, some energy is dissipated. That energy is charged into the voltage. Charge into voltage is the energy. The charge is CL times VDD. The voltage is VDD. So the energy that is dissipated in every pulse is CL times VDD squared. This square dependence on the voltage is very important when we think about power and what we can do to reduce power. Is one of the big motivations for supply voltage to keep decreasing as the IC technology advances. For example, at 130 nanometer technology, we had supply voltages were of the order of 1.5 volt or 1.2 volt. Now they're down to 0.8 volt. And one of the big motivations to reduce supply voltage is because of the square dependency of energy on voltage. Now, this is the energy dissipated every time there's a pulse. Power is energy dissipated per second. So we have to see how many pulses there are per second to determine power. If there are NP pulses per second at the gate's output, then the switching power of the gate is energy, that's CLVDD squared, times number of pulses per second, which is NP. And so this is the fundamental equation for power. P is CVDD squared times pulses per second. For a clock with frequency f, number of pulses per second is f by definition of frequency. Frequency is number of clock pulses per second. So switching power dissipation of a buffer driving a clock would be the load capacitance of that buffer, CL, times square of the volt power supply, VDD squared, times the clock frequency f. So this is straightforward for a clock. For data signals, things are a little bit unclear because it's not easy to tell how many pulses there are per second at the output of any combinational gate or even any sequential gate. So at the output of any gate, what are the pulses per second is not that clear. Particularly not clear for combinational gates. For sequential gates, they will only switch at clock edges. So the activity of sequential gates is related to the clock frequency in a much more direct manner. For data, for the outputs of combinational cells, it's very unclear what how many pulses there are per second. So we define an activity factor alpha, where alpha is number of pulses at the output of a logic gate divided by the clock frequency. Okay, and so if you look at if you replace for NP in the equation for power, then you get power is CL VDD squared times f alpha. F is the clock frequency, alpha is the activity factor. And again, activity factor is number of pulses per second divided by the number of pulses per second of the clock, which is f. So NP over f is alpha. Power therefore is C VDD squared f alpha. And this is the fundamental equation that's used by all tools when they're computing power dissipation in a logic circuit. Generally, like sort of empirically, we see that alpha is much less than 1 for most signals, for most data signals, and therefore the clock is the most active signal in the circuit, because for a clock, the activity factor is obviously 1, because NP over F is F over F for a clock. So activity factor for a clock is 1, and the clock is generally the most active signal. For all the other data signals, we sort of usually use a sort of rule of thumb that, or a thumb rule, that alpha is about 20%, 0.2. Okay, so with that background, we can look at what other techniques we can use for reducing power. We know what power depends on. Power depends on C VDD squared F alpha. To reduce power consumption of a chip, we can try to reduce all of these factors. We can try to reduce the load capacitance that cells drive. So in fact, for that is a technique that is used sometimes wherever we find that there are some, if we know that some logic is very active, there's a lot of pulses, we can try to reduce the wire capacitance for that logic. And in general, we should always use the lowest drive strength cells so that the load capacitance is low. If you use an unnecessarily high drive strength cell, then its input pin caps will be higher, and therefore the load capacitance will be higher, and it will result in higher power dissipation. So CL, the load capacitance reduction is one of the things we can try to do to reduce power. Then reducing the supply voltage is a very impactful, because there's a square dependency on supply voltage. So reducing supply voltage is the other thing that can be done. And at times, chips are designed to deliberately run at very low voltages. The problem with reducing voltage is that when you reduce voltage, you also reduce the speed of the circuits. In other words, the delays of combinational cells and sequential cells will go up when the supply voltage is reduced. So even though supply voltage reduction can reduce power, it also comes at the cost of reduced clock frequency or reduced performance, since all the delays increase. And clock frequency can be decreased if it is possible. Sometimes that is not possible because we want a very high clock frequency for the performance we need from a chip. And then the activity factor is the final thing that we can try to reduce. Okay. So in these four factors, you see a load cap, power supply voltage, clock frequency, and alpha. Let's say that the clock frequency is a given, and that's not something we can reduce because that is one of the sort of requirements for the chip. So the clock frequency may be fixed. The load capacitances of individual standard cells, that's something that one can adopt design practices that keeps that as low as possible. The supply voltage, reducing that comes at a cost, and we may not be able to reduce it. So the real important ones we can try to play with are load capacitance and activity factor alpha. And then as far as the supply voltage is concerned, we do things like have different supply voltages for different portions of the chip. Wherever you have low performance or you don't need a high clock frequency, we can run the circuitry at lower voltage. Wherever you need high clock frequencies, we would need to run the circuitry at higher voltage. And so there are chips done today where you have multiple supply voltages just because of this square dependency on supply voltage.